It's one of life's little ironies that our understanding of the edge of our solar system hasn't been advanced by new cutting-edge technology, but by an old machine. The Voyager probes, which were launched in 1977, have onboard computers with less memory than the key fob for your car. To this day, these spacecraft continue to use 8-track magnetic tape from the 1970s, which is outdated even by the standards of the time. This makes the technology in these probes older than many of the people watching this. This paradox is part of the strange nature of deep space exploration. Vast distances and incredibly long travel times can result in technology becoming outdated long before it reaches its final destination, which is a unique challenge for space missions like Voyager. Despite all the advancements in modern space technology, these old spacecraft have still managed to achieve incredible things and provide us with valuable information about the outer reaches of our solar system. The juxtaposition of new theories and old technology remains one of the more ironic aspects of the Voyager missions, making their accomplishments even more extraordinary. I'm Alex Mullen, and you're listening to the Astrum Podcast. Today, we'll explore the technology of the Voyager probes and dive into how a series of innovative engineering choices helped make these probes one of the most successful space missions in history. Although Voyager 1 and Voyager 2 were originally designed for a 5-year mission to study Jupiter, Saturn, and their moons, the team behind these spacecraft was farsighted. They made strategic design decisions that allowed the probes to keep going well beyond their initial objectives. Their ability to adapt to challenges and pursue additional scientific goals was key to the longevity of the mission. By thinking beyond the immediate mission, the engineers and scientists ensured that the Voyagers would continue to deliver vital data long after their primary tasks were complete. These smart engineering decisions have allowed the probes to continue providing groundbreaking discoveries from the farthest reaches of our solar system. The probes' continued operation, despite their age and limitations, speaks to the ingenuity behind their creation. The Voyager mission has taught us important lessons about the importance of planning, innovation, and flexibility in long-term scientific endeavors. After completing their primary objectives at Jupiter and Saturn, Voyager 2 was sent on additional flybys of Uranus and Neptune, extending its mission far beyond initial expectations. These extra flybys added decades of valuable scientific data to what was already a wildly successful mission. Once these objectives were achieved, NASA announced the start of the Voyager interstellar mission, which aimed to explore the outer limits of the Sun's sphere of influence and ultimately venture beyond into interstellar space. This was an even more ambitious goal, taking the probes off the ecliptic plane and into unknown regions of space. These areas included the termination shock, a boundary where the solar wind slows down, and the heliosheath, a dense, hot region surrounding the solar system's boundary. The mission's ultimate goal was to reach the heliopause, the point where the Sun's influence gives way to the surrounding interstellar space. This transition into interstellar space was historic, marking the probes as the first human-made objects to leave the solar system. The decision to continue the mission beyond its original scope was a bold one and would ultimately provide humanity with its first direct exploration of interstellar space. These accomplishments have significantly expanded our understanding of our place in the universe. One of the most important engineering decisions in making these probes capable of such a long mission was the choice of energy source. Each Voyager probe is equipped with a radioisotope thermoelectric generator, RTG, which converts heat generated by the decay of plutonium-238 into electrical power. These generators provided 157 watts of electrical power at the time of launch, which was enough to run instruments like cameras and scientific equipment, along with communication systems. At the time, this was a breakthrough technology that ensured the spacecraft could continue functioning far beyond the reach of the Sun's energy. While the power output of the RTGs has gradually decreased over time as the plutonium decays, the technology has been remarkably reliable. Despite the steady decline in power, the generators are still able to provide enough energy to keep the essential systems on the probes running, and NASA estimates that they will continue to function until at least 2025. The long-lasting power supply was an essential feature, as the distance from the Sun meant that solar power was not an option. The decision to use an RTG allowed the mission to last far beyond its initial design, making it possible for the probes to continue sending valuable data back to Earth even as their power slowly diminished. When the Voyagers launched in 1977, NASA was fortunate enough to have a rare opportunity. The planets in the outer solar system were in a once-in-176-year alignment that would allow the probes to visit Neptune and Uranus with minimal course adjustments. This rare alignment meant that the probes could take advantage of gravity assists from each of the outer planets they visited, giving them a boost in speed and reducing the amount of fuel required for the mission. This alignment provided a unique chance to explore the outer planets, but it also imposed a strict deadline. There wasn't enough time to plan follow-up missions, and NASA was unable to secure the funding needed for a more extensive mission. So the probes had to be designed for maximum efficiency and longevity within that narrow window. The decision to make the most of this rare alignment had a profound impact on the mission, enabling the probes to travel faster and more efficiently than they otherwise could have. This allowed them to complete their objectives and extend their mission far beyond the original scope, ultimately leading to the probe's entrance into interstellar space. To take full advantage of the rare planetary alignment, the Voyager team had to design the probes for a much longer mission than initially planned. They knew the probes might not receive the funding necessary for follow-up missions, so they built the spacecraft with redundancy and durability in mind. Each probe carries 11 scientific instruments, most of which have backups to ensure that the mission could continue even if a system failed. Additionally, many of these instruments can be toggled on and off to conserve power over the long journey. The probes were also equipped with gyroscopes for stabilization, which allowed them to maintain their orientation in space. Furthermore, they had 16 hydrazine thrusters, including 8 backups, to ensure they could adjust their course and maintain proper orientation. The importance of these backups was demonstrated when Voyager 2's main thrusters stopped working after 37 years. The backup thrusters, which had been inactive for decades, were successfully activated and kept the probe operational. These design choices were critical for the longevity of the mission, and the success of the backup thrusters demonstrated just how well the probes were built. The foresight to include redundancies and durability in their design is part of what has allowed the Voyager. Another crucial aspect of the Voyager probes was their custom-built onboard computers. While these computers may seem antiquated by modern standards, they were cutting-edge technology at the time of the probe's launch. The probe's wide-angle and narrow-angle cameras are controlled by a computer command subsystem, which has fixed programs to handle fault detection, correction routines, and other essential functions. These systems helped ensure the probe's continued operation throughout their long journey. The computers also included an attitude and articulation control subsystem, which ensured the probes remained oriented properly in space. This was vital because, without proper orientation, the probe's high-gain antennas wouldn't be able to send or receive signals from NASA's deep space network. Given the immense distances involved, the probe's transmitters only have the power of a refrigerator light bulb, so their radio signals become faint whispers that are nearly impossible to detect. Without the attitude control system, the probes would have been unable to communicate effectively. This is why the probe's onboard computers, though primitive by today's standards, were one of the most important elements of the mission's success. They played a critical role in maintaining communication and ensuring the spacecraft's continued operation. These onboard systems were designed with great care to handle the challenges of deep space communication and provide the longevity needed for the mission. In addition to the high-gain antenna, the Voyager probes use an 8-track digital tape recorder, DTR, capable of storing 536 megabits of data for future transmission. This data storage was an essential component of the mission, allowing the probes to store images and other scientific data until they were able to transmit it back to Earth. While the DTR was a huge improvement over earlier probes which had no onboard data storage, it still pales in comparison to modern storage devices. Despite its limited capacity, the DTR was built to last and to withstand the harsh environment of space. The manufacturer of the DTRs claimed they could process over 4,000 kilometers of tape without showing visible wear and tear, which is impressive considering the extreme conditions these devices had to endure. These storage devices had to withstand the vacuum of space, extreme temperature fluctuations, and radiation, and they performed without fail throughout the mission. Voyager 1's DTR is still operational, continuing to send back data even after decades in space. Voyager 2's DTR was turned off in 2007 to conserve power, but these devices have far exceeded their expected lifespan. Despite their modest capabilities, The DTRs played a crucial role in ensuring the probes could continue their mission and provide valuable data. These devices are a testament to the foresight and engineering brilliance that went into designing the Voyager spacecraft. Durability was one of the most important factors in the planning of the Voyager missions. There were numerous uncertainties in such a long mission, particularly in the spacecraft's path through the asteroid belt on their way to Jupiter. Scientists once believed that the asteroid belt contained enough debris to damage or destroy any spacecraft that attempted to pass through it. However, previous missions like Pioneer 10 and 11 had successfully passed through the asteroid belt without incident, which gave the Voyager team confidence that their probes could do the same. Despite the risk, both Voyager probes passed through the asteroid belt unscathed, proving that the region is largely empty space, rather than the dense asteroid field that scientists once imagined. This discovery was a huge breakthrough and was made possible by the Voyagers. Their successful passage through the asteroid belt helped change our understanding of that part of the solar system and contributed to the probe's reputation for durability. Despite facing many challenges, the Voyager probes continued to perform far beyond expectations. They not only survived the risks of deep space but also contributed invaluable knowledge that would have been impossible to gather without these resilient spacecraft. Even with all these successes and the probes performing far better than anyone had expected, there were still concerns about what would happen when the spacecraft encountered the extreme cold of interstellar space. As the probes moved farther from the Sun, NASA had to turn off some of their heaters to conserve power. These heaters were critical to ensuring the instruments and systems continued to function in the frigid temperatures of space. When the heater for the cosmic ray detector was switched off 2 years ago, the temperature of the instrument plummeted by 70 degrees Celsius, and many scientists feared it would break down. Sending a repair team 23 billion kilometers into space was, of course, not an option, so there was no way to fix any malfunctioning equipment. Despite these fears, the cosmic ray detector continued to function, surprising engineers and scientists alike. This resilience is just another example of how the Voyager probes have consistently exceeded expectations and defied the odds. Even with power running low and temperature extremes threatening their instruments, the Voyagers have kept transmitting data and functioning well beyond their expected lifetime. This extraordinary longevity is a testament to the exceptional engineering that went into designing these probes. The fact that the probes have lasted so long, 45 years, is a remarkable testament to their resilience and the ingenuity of their engineering. However, as with any mission of this scale and ambition, there are always unforeseen challenges. For example, Voyager 1 began sending scrambled signals in 2022, puzzling scientists. While the probe itself continued to function normally, its telemetry data became corrupted, leading to a loss of information about its position and status. This unusual behavior was eventually traced back to a malfunction in the attitude and articulation control system. Though the probe continued to respond to commands and send back useful data, it seemed to have lost track of its exact orientation in space. Engineers worked quickly to switch to a backup system to mitigate the issue. This was an important lesson in the realities of space exploration, where technology, no matter how carefully designed, will eventually encounter unforeseen problems. Despite this setback, the fact that the probes are still functional and capable of providing data after so many years is a testament to their extraordinary design and the ingenuity of the engineers who created them. Despite these setbacks, Voyager 1 has traveled farther than any other human-made object, including its twin Voyager 2. The technology, though rudimentary by today's standards, has accomplished far more than anyone initially expected. The discoveries made by the probes have provided humanity with invaluable insights into the outer reaches of our solar system and beyond. When the time comes to say goodbye to the Voyagers, we will apply the engineering lessons learned from their mission to future projects. One such proposal is a new interstellar probe from the Johns Hopkins Applied Physics Laboratory, which could launch in 2036 and reach interstellar space within 15 years. This mission would be a remarkable achievement, just as the Voyager probes were in their time. However, even this new probe, like its predecessors, will eventually become outdated and obsolete.